Hello everyone, welcome in my YouTube channel MechE-FUNdaMENTALs. The topic of this video is the resultant force. In the series of Fundamental of Mechanical Engineering, the topic of this video is the resultant of coplanar force system. This topic comprises types of coplanar force system, composition of forces, resolution of forces, parallelogram law of forces, method of resolution, Varignon's theorem, and at last some numericals. Force system. When two or more than two forces act on a body, it is known as force system. The classification of the force system, that is of two types. The first is coplanar force system and the second is the non-coplanar force system. When we do the classification of force system, then we use the characteristics of the force, that is the line of action. So when the line of action of all the forces lie in a single plane, then it is called as coplanar force system. You see in this diagram, we have the three forces. The line of action of all the three forces lie in this single plane. So this is the example of coplanar force system. When the line of action of all the forces do not lie in one plane, it is called as non-coplanar force system. You see in this example, the line of action are in the different planes. So this is the example of non-coplanar force system. In coplanar force system, again we have the different types. Because the line of action lie in a single plane, but still we have the different arrangements. When the line of action lie in a single plane and the line of action of all the forces is same, then it is called as coplanar collinear force system. When the line of action of all the forces lie in a single plane and we have a common intersection point, then it is called as coplanar concurrent force system. When the line of action lie in a single plane and they are parallel to each other, then it is called as coplanar parallel force system. When the line of action of all the forces lie in a single plane and we are not getting a common intersection point, then it is called as coplanar non-concurrent force system. The next is the principle of superposition of forces. The combined effect of any force system is called as the resultant force, and the principle of finding that resultant force is called as the principle of superposition. So this principle is used to determine the resultant of any force system. Now in this example, this is a boat in which two forces are acting, P and Q, and R is the resultant of these two. Or we can say that the combined effect of P and Q, that is given by R. So to find out that resultant, we have to do the vector addition of P and Q because the force is a vector quantity. So the combined effect, which is the resultant force, that is given by P plus Q. So that is a vector addition of P and Q. Resolution of a force into components. In this, a single force can be divided into two components which are perpendicular to each other in such a way that the effect remains same, and it is called the resolution of a force. Now you see in this diagram, a force F is there, and Fx and Fy. These are the two components of this force F. Fx is the component in the x direction or in the horizontal direction. Fy is the component in the y direction or in the vertical direction. So Fx and Fy are the component of this force F. In other words, we can say that F is the resultant of these two forces, because we can replace these forces by a single force F, or we can remove or replace this force F by its component also. So it is applicable vice versa. Now to find out Fx and Fy, so that we can find out by using the simple geometry and the trigonometry concept. So in this force F, we construct a right angle triangle like this. So this is the force F. Its horizontal component is Fx and the vertical is Fy. So now we use the simple trigonometry. So the angle from the horizontal is theta. So cos theta, that is Fx upon F. So we get Fx, that is F cos theta. Then sin theta is Fy upon F. So we get Fy is equal to F sin theta. So In this way, we can find out the horizontal and the vertical component of a force, and that is the resolution of a force. Now, the methods of finding the resultant of a coplanar concurrent force system. So in this, we have the two methods. The first one is the graphical method, and the second is the analytical method. Graphical method means we construct some geometry, and by some measurement, we are getting our required objective. And in the analytical method, we are using some formula. So the graphical method, again, we have the three. First is the parallelogram law of forces. Second is the triangle law of forces. Third is the polygon law of forces. In analytical, again, we discuss parallelogram law of forces and the method of resolution. So parallelogram law we can use graphically as well as analytically. Now the first one, that is the parallelogram law of forces. In this law, we have to take two forces at a point. So P and Q, these are the two forces which are acting at a point, that is O. And let us suppose the angle between these two forces is theta. So this law says that we have to construct the two adjacent sides of a parallelogram by using the given two forces. So first we take this force P and we draw a side OA like this. So this line OA represents the force P by magnitude as well as by direction. Then we have to draw the adjacent side of that parallelogram. So we have to start from O and we have to draw the vector force, that force vector Q. So OB. So this is the force Q by magnitude as well as by direction. And the angle between these two forces, that is theta, so that we have to maintain. So in this way, we construct the two adjacent sides of a parallelogram. These are the two adjacent sides by using force P and Q, and by magnitude as well as by direction. Then we have to complete that parallelogram, and we know the geometry of the parallelogram. So accordingly, we complete that parallelogram. So when we complete that parallelogram, then the diagonal of that parallelogram, which intersects the above two adjacent sides, represent the magnitude and the direction of that resultant. So simply you have to measure the diagonal OC, that you give the magnitude, and by measuring this angle alpha, you are getting the direction of the resultant from P. So this is the graphical way to determine the resultant, its magnitude and the direction by using parallelogram law of forces. The next is the triangle law of forces. Again, in this law, we have to use two forces P and Q as we do in the parallelogram law also. And these two P and Q forces are acting at a point O. Again, the angle between these two, we take theta. Now what we do in this law? First, we have to make the two sides of a triangle in an order by using these two forces. So first we draw this P. So OA, this is the side of that triangle which represents the force P by magnitude as well as by direction. Then the next force, that will start from A, because now we have to make the sides in an order. So the next force vector Q, that will start from A, so that we make the side in an order. So we draw a line AB at an angle of theta from the direction of P, because the angle between P and Q, that is theta. So the length AB represents the magnitude and this theta is the direction. So OA and AB are the two sides of a triangle in an order by using these two forces P and Q. Now we have to close that triangle. When we close that triangle, then this closing side OB, opposite in order, that will give you the resultant by magnitude as well as by direction. So by simple measurement of OB, you are getting the magnitude, and by measuring this alpha, you are getting the direction. So in triangle law of forces, two forces at a point are represented by two sides of a triangle in an order by magnitude as well as by direction. Then the closing side opposite in order give you the magnitude and the direction of the resultant. So this is the triangle law of forces. The third, that is the polygon law of forces. In this, generally we talk about when we have the involvement of more than two forces. You see in the parallelogram law and the triangle law, we talk about the resultant of the two forces. But when the requirement is to find out the resultant, forces are more than two. You see here in this diagram, we have the five forces, F1, F2, F3, F4, F5. And definitely we have some angle in between these forces also. So what we do in this polygon law of forces? Now, by using these given forces, we have to construct the sides of a polygon in an order. So let us suppose first we pick force F1. So we draw a line OA, which give the value of F1 by magnitude as well as by direction. Then as we draw the sides of the polygon in an order, so the next force vector that will start from A. With that magnitude, we draw a line AB, and definitely we have to maintain that angle also in between F1 and F2, that angle which is given to you. Then AB, that represents force F2. Then again in an order we have to draw the next side. So we start from B, and now we have to draw this F4, and this is some particular angle. With that angle we draw a line BC like this. So this BC gives you the F3 force by magnitude as well as by direction. Then we draw force F4 again in an order of that. Then we start with C and we draw CD, and definitely we have to maintain the direction also that you have to see here. So CD, that is F4. Then again with respect to the line of action of that F4, we have some angle, and then with that angle we draw again a side, that is DE, which is represented F5. So now by these 5 forces we draw the sides of a polygon in an order, that is OA, AB, BC, CD and D. Now we have to close that polygon, starting point to the end point. So this closing side of that polygon, opposite in order, give you the resultant by magnitude as well as by direction. So you can measure this angle with respect to F1, you get the direction, and when you measure the length OE, that you give you the magnitude of the resultant. So this is the way to determine the resultant by using the polygon law of forces, when generally the forces are more than 2. So according to the polygon law of forces, we represent the sides of a polygon in order by using the given forces by magnitude as well as by magnitude and the direction. Then the closing side of that polygon, opposite in order, give you the resultant by magnitude as well as by direction. The next is the analytical method. Analytical method means now we are using some formula. So the first one, that is the parallelogram law of forces. So already we discussed the graphical way to use this particular law. Now you see in this diagram. So the first force, that is P, the second force is Q. They construct the adjacent sides of the parallelogram. So these are the adjacent sides of the parallelogram. And that parallelogram is O, A, B, C, O. So this is the parallelogram we construct by using these two as adjacent sides. Then this diagonal OA give you the resultant by magnitude as well as by direction. So now for analytical method we have to develop some formula. So we have to do a construction. From B we have to drop a perpendicular in the extension of this OC. We extend this OC line like this, and we drop a perpendicular from B in this extension, that is 90-degree angle. So that construction we have to do. Now see, this OA is actually representing force vector Q, and this CB is also same Q, because the length is same, the direction is same. So this OA, that is representing force vector Q, as well as this CB also represent force vector Q. And this Q, we can take two components, one the horizontal, that is Q cos theta, and the vertical, that is Q sin theta. So that is by the method of resolution or by using some simple trigonometry. So now to find out the magnitude of the resultant, we have to use this right angle triangle you see here, this OMB. So this right angle triangle you see, OMB. You have to see this right angle triangle. In this right angle triangle we have to use the Pythagoras theorem. So this OB square, that is equal to OM square plus MB square if you use the Pythagoras. So what is OB? That is R, so R square. What is OM? That is P plus Q cos theta, so this is P plus Q cos theta whole square. And what is MB? That is Q sin theta, so that is Q sin theta whole square. So by using that Pythagoras, so again we have to expand the term, then finally we are getting this expression. So R is equal to under root of P square plus Q square plus 2PQ cos theta. So by using this we can find out the magnitude of the result. To determine the direction, so now we have to talk about this alpha value. So again in this right angle triangle, so tan alpha will be MB upon OM. And what is MB? It is Q sin theta. And what is this OM? That will be P plus Q cos theta. So alpha, that is equal to tan inverse of Q sin theta upon P plus Q cos theta. So here this expression gives you the magnitude and this gives the direction from the direction of P. So here simply we put or feed the value of P, Q and theta in both the expression and we are getting the magnitude and the direction. So here we are not measuring anything, we are not constructing any geometry. Simply by putting the values in these two formulas we are getting the thing. So that is the analytical method of using parallelogram law of forces. The second, that is the method of resolution of forces, very popular method. Now see, this is the force system which is given to us. So these are the number of forces F1, F2, F3, F4 and these angle alpha 1, alpha 2, alpha 3, alpha 4. Now to use this method of resolution we have the different steps. So the first step, that is the resolve all the forces along the horizontal x-axis and the vertical y-axis. So that we have to do. So one by one we resolve these forces to understand this method of resolution. So first you see this force F1. This force F1. You see this force F1. So first we resolve this force in horizontal and the vertical direction. So this is F1 cos alpha, horizontal component, and this F1 sin alpha, that is the vertical component of F1. This angle is alpha 1, so this angle is also alpha 1 by geometry, and we resolve that force F1 cos alpha 1, F1 sin alpha. In the same way, we resolve force F2, that is in the second quadrant. So this is the horizontal component of F2 and this is the vertical component of F2, F2 cos alpha 2 and F2 sin alpha 2. Then we resolve this F3, that is in the third quadrant. So F3 cos alpha 3 is the horizontal and F3 sin alpha 3 is the vertical component. Now the fourth force F4 in the fourth quadrant, its horizontal component is F4 cos alpha 4 and the vertical component is F4 sin alpha 4. So initially we have 4 forces. Now by resolving horizontal and the vertical direction, now we have 8 number of forces. So definitely the number of forces are increased, but that is the first step that we have to do in method of resolution. The net force along the plus x-axis and summation Fy, that is the net force along the plus y-axis. So to find out the net force along the plus x direction, we have to observe the horizontal forces or the x direction forces in this force system. So if you observe the horizontal forces in components, so F1 cos alpha 1 is the first horizontal force, F2 cos alpha 2, that is the next one, F3 cos alpha 3 is the third one, and F4 cos alpha 4 is the fourth one. So we have the 4 forces in the horizontal direction and in the x direction. You see these 2 forces are in the rightward direction, this is the right direction. This is the right direction force in the horizontal, and these 2 forces are in the negative x direction, But now your objective is to find out the net force towards right. So what you do? You have to add these 2 forces, and in that you have to subtract these 2 forces. So you see the expression of summation fx now. Summation fx here. So it is F1 cos alpha 1, the first component, F1 cos alpha 1. This is F1 cos alpha 1. Then F2 cos alpha 2, that is with minus sign, minus F2 cos alpha 2. Then F3 cos alpha 3, again minus sign, minus F3 cos alpha 3. And next is F4 cos alpha 4, it is plus F4 cos alpha 4. So by this, we find out the net value of the force along the plus x direction. Okay. In the same way, we have to find out the net vertical force in the upward direction. So now we have to see the vertical forces. So that is F1 sin alpha 1, F2 sin alpha 2, F3 sin alpha 3 and F4 sin alpha. So these 4 are the vertical forces. But you see the direction, that is upward. This is upward. These 2 vertical forces are downward. You see the direction. And your requirement is to find out the net vertical force in the plus y direction. So you have to add these 2 forces, in that you have to subtract these 2 forces. Now you see the expression. So F1 sin alpha 1, the first term, F2 sin alpha 2, again that is plus F2 sin alpha 2, then F3 sin alpha 3, that is minus F3 sin alpha 3, and this is minus F4 sin alpha 4. So in this way you find out the net vertical force upward. So initially you have 4 forces, you resolve forces, then you get 8 number of forces, and now do the algebraic summation along the plus x direction and along the plus y direction. Now you have only 2 forces, net summation fx and summation fy. So in this way in the method of resolution, whatever the number of forces, that you can reduce in two forces only. Now we have only two forces, the summation fx and summation fy, and definitely the angle between these two, that will be 90 degree. So now we can use the parallelogram law of forces where theta is 90. So r, that will be under root summation fx square plus summation fy square, and the direction, this alpha, that is tan inverse of summation fy upon summation fx. So in this way we find out the magnitude and the direction of the resultant. The next is, the last step is to sense the correct quadrant of the resultant, because r, that is under root of summation fx square plus summation fy square, and alpha, that is tan inverse of summation fy upon summation fx. In that we are putting the mode value, it means we are putting the positive value, so r and alpha always positive. But the quadrant is decided by the sign of summation fx and summation fy. If both summation fx and fy is positive, then the resultant, that will be in the first quadrant. When summation fx is negative and summation fy is positive, then the resultant will be in second quadrant. When both are negative, summation fx as well as summation fy, then the resultant is in the third quadrant. When summation fx is positive and summation fy is negative, then the resultant is in the fourth quadrant. So you find out the magnitude and the direction by using the parallelogram law of forces, where theta is 90, and you put summation fx, summation fy positive values, but to find out the correct quadrant, you have to check the sign of summation fx and summation fy. Now in the coming slide, I will discuss the one numerical, in that you better understand the same thing. The next, that is the Varignon's theorem, which is also known as the principle of moment. So this theorem is also used to determine the position of the resultant in coplanar non-concurrent force system. So that is the reason why I take this topic here again. So according to this theorem, the net moment of any coplanar force system about any point on that plane is equal to the moment of their resultant about the same point. Now with the help of this diagram we can better understand. You see, we have the two forces, the fx and fy, and f is the resultant of these two forces. So according to this Varignon's theorem, the net moment about any point of any force system, let us suppose fx and fy are the two forces of that force system. So the moment about this point, that will be mx and my. Mx is the moment of fx and my is the moment of fy about this point. Okay, and the moment of f, that is m. So in one hand we have to talk about the moment of that force system about that point. In other hand we have to talk about the moment of their resultant about the same point. And the Varignon's theorem says that the net moment, it means mx plus my, and the moment of the resultant, that is m. So m, that is equal to mx plus my. And here you see the mx value, this is fx, this is line of action, dy is the distance, so that is fx into dy, that is value mx, and my, that will be fy into dx. So the net moment of any given force system about any point is equal to the moment of their resultant about the same point. And definitely, because the resultant force will give the same effect. So when we talk about the moment about any point of any force system, means we are talking about the rotational tendency of that force system about that point. And definitely the resultant force also gives the same rotational tendency about that point. So this is the Varignon's theorem. Now to prove this Varignon's theorem, first we have to understand the graphical representation of moment. It means we have to show the moment value with respect to geometry. Now see this diagram. We have a force P, which is represented by a side AB or a line AB. So this AB represents the force P by magnitude as well as by direction. And we have to take the moment about O. So this is the force which is represented by AB, and this is the point about which we take the moment. So as per the moment definition, force is P about O. So that is the force P. The second is, from that point you have to draw a perpendicular to the line of action of that force. This is the line of action of that force, and you draw a perpendicular. So that is OC. OC. So that will be P into OC. So that is the moment of this P about O. And you know that this force P is represented by AB. So in place of P I can write AB. So that will be the moment, that will be AB into OC. Now you see this triangle which we construct, take AB as a base and O as a vertex. So the area of this triangle, that is given by half into base into height, so half into AB into OC. When you compare these two terms, then you easily observe that, so AB into OC, that is twice of this. When you multiply this by 2, then you are getting AB into OC. So we can say that the moment of force P about O, that is also equal to twice of the area of this triangle ABO. So finally we can conclude by that remark, moment of any force about any point is equal to the twice of the area of the triangle whose base is the force and point is vertex. So this is the way to represent the moment graphically, and that we have to use in the proof of Varignon's theorem. So I discussed before. Now this is the proof of Varignon's theorem. Now we can easily understand. So here we take F1 and F2, these are the two forces, and R is the resultant of these two. And O is the point about which we are using the Varignon's theorem. So what we have to do, or what we want, that the moment of F1 and F2 about O, that is equal to the moment of the resultant about O. So that we have to prove. So now one by one we talk about the moment of forces. So first we take this F1. F1 is the force. It is represented by AB. And O is the point, it means that is the vertex. So AB is the base, O is the vertex. So that is the moment of force F1 about O. So as per the graphical presentation of the moment, so the moment of this F1 about O, that is the area of this, twice of the area of this triangle ABO. So M1, that is equal to twice of area ABO. Now we have to take the moment of this F2 about O. So F2 force, that is represented by AD. O is the point. So AD is the base, O is the vertex. Then the moment of F2 about O, graphically that will be twice of the area of the triangle ADO. So that is twice of area ADO. Then we have to talk about the moment of R about O. R, that is represented by AC. So AC we take as a base, O as a vertex. So what is the area of the triangle? That is ACO. So now we have to make the twice of this area, twice of area of ACO triangle. So we get the moment of the resultant about O. So this is the way to determine the moment graphically. So now to prove the Varignon's theorem, we have to add equation 1 and 2. So M1 plus M2, that will be twice of area ABO plus twice of area ADO. Now you see this triangle ABO, and this triangle you see that is DCA, this triangle, these two triangles. This triangle I will actually has it. This is the triangle, this is the ABO, and I take the second triangle, that is this is DCA, or these two triangles DCA and AB. You see this is the ABO, the second is DCA, this is DCA. You see the area of these two triangles, that will be same. You see the base of the first triangle, that is AB, the base of the second triangle, that is DC. Both have the same length. It means the base is same. When you see the height of both the triangles, so this is the height of both the triangles. So this for this triangle, this is the height of the triangle, vertex to its base. And you see if this triangle, this is the base and this is the vertex, so again the distance is same. So height is same. So the area of triangle ABO, that is the area of the triangle DCA. So in place of ABO, we can put DCA. So twice of area DCA plus twice of area ADO. And you see this DCA and that ADO. When you add these two triangles, this is the first triangle. To better understand, I will let us suppose I do this is the triangle and this triangle. When you add these two triangles, so you get this complete one, ACO. So DCA plus ADO, that will be ACO, and 2 is common. So that is twice of area of ACO. And you see equation 3 and 4. Both are same. But the third, that is the moment of the resultant about O. And this is the sum of the moment of M1 and M2 about, sorry, F1 and F2 about O. And both are same. So finally you can say that M1 plus M2, that is equal to MR. So this is the proof of Varignon's theorem. Now as we get the net horizontal force and the net vertical force, so we have only two forces. One that is horizontal towards right, the next is vertically upward. So by using the parallelogram law of forces, we find out that resultant by using the formula R is equal to under root of summation fx square plus summation fy square. and theta, that is the direction, tan inverse of summation Fy upon Fx. So this is the magnitude and this is the direction. But you see the sign of summation Fx is negative. So summation Fx is negative and summation Fy is positive. So the resultant that will be in the second quadrant. So this is the final presentation of the resultant. The next problem, that is the resultant force of a non-concurrent force system. So this is the problem. In the square plate, we have the four forces: 1.5 kilonewton, 2 kilonewton, 1 kilonewton, and 2 kilonewton. And we have to find out the resultant of the four forces which are acting in this particular square plate in their vertex. So in method of resolution, the first step is we have to resolve these forces. So these red arrows are actually the components. So 1.5 kilonewton, this angle is 45 degrees. So these are the two components, 1.4 cos 45 and 1.5 sin 45. This 2 kilonewton, again we have the two components, 2 cos 30, 2 sin 30. 1 kilonewton, these are the two components, 1 cos 45, 1 sin 45. 2 kilonewton, that is 2 cos 30, 2 sin 30. So initially we have 4 forces, and by resolution now we have 8 forces. The second step, now we have to find out the net vertical force towards right and the net vertical force upward. So convention is rightward force we take positive and leftward force we take negative. So in the first we have to identify the horizontal forces. So in these components, the horizontal forces first we have to identify. 2 cos 30 is horizontal, 1 cos 45 horizontal, 2 cos 30 horizontal, and 1.5 cos 45 horizontal. So we have 4 horizontal forces. These two forces, that is towards right. You see the arrow. And these two forces, that is in the negative x direction, or these are leftward. So to find out the net horizontal force towards right direction, this is the net force requirement. So that will be minus 2 cos 30 minus 1 cos 45 plus 2 cos 30 plus 1.5 cos 45. So that is the net value along the plus x direction. Now to find out the net vertical force upward. So again, we have to identify the vertical forces, and now you see the vertical forces: 2 sin 30, 1 sin 45, 2 sin 30, and 1.5 sin 40. Again, we have the 4 vertical forces. You see these two forces are upward and these two forces are downward. So what is the net value? So 2 sin 30, that is minus 2 sin 30 downward. 1 sin 45, that is upward, so that is plus 1 sin 45. 2 sin 30, it is upward, so plus 2 sin 30. Minus 1.5 sin 45, because that is downward. So that is the net value, minus 0.354, but that is the net value in upward direction. So initially 4 forces. By resolution we get 8 forces, but by finding the net horizontal force in plus x direction, the net vertical force in plus y direction, now we have only 2 forces. So in this way, in the method of resolution, whatever the number of forces, we can reduce it in 2 forces only. Now we can use the special case of the parallelogram, then we can find out the resultant by root summation fx square plus summation fy square, and we find out the direction alpha is tan inverse of summation fy and summation fx. And to sense the correct quadrant of the resultant, we have to check the sign of summation fx and summation fy. So summation fx is positive and summation fy is negative. So the resultant that will in the 4th quadrant. So this is the resultant and this is the direction of the resultant. Now the position of the resultant. So this is the requirement of the resultant of coplanar non-concurrent force system. Because in this, the forces are in such a way that we are not getting a common intersection point. As in the concurrent force system, all the forces are at a point. Let us suppose this is the first force, this is the second force, this is the third force. And the resultant, definitely that will also act on that point. So there is no requirement to find out the position of the resultant. So in concurrent force system, the magnitude and the direction is sufficient to define the resultant completely. But in the non-concurrent force system, if you see, this is the resultant and it is the direction from horizon. So where you put that? Where we give the position? So we have the infinite number of the possibility to draw that magnitude and the direction. So let us suppose this is the resultant. You can draw here, you can draw here. But the resultant has some certain position. So we have to give the position of the resultant so that the resultant completely defined. So in other words, we can say that in coplanar non-concurrent force system, the resultant is completely defined by its magnitude, direction as well as the position. And to position, we are using the Varignon's theorem. For that we have to give the position of the resultant with respect to some point, because the position is always relative. So what we are doing, we are giving the position of the resultant with respect to A. So this is the A point. And let us suppose that distance is D. Now we are using the Varignon's theorem about the point A. So in Varignon's theorem, what we have to do, we have to find out the moment of all the forces about A. And on the other hand, we have to find out the moment of the resultant about the same point, and we have to equate. So first we have to take the moment of all the forces about A. So that is the left side, net moment of all the forces about A. And the right side, moment of the resultant about A. So about A, we write the expression of the moment of all the forces. And you see, let us suppose if a force is acting like this, and you have to take the moment about here in its line of action, any point in the line of action. So definitely that force will not give any moment about the point which is passing through in its line of action, because the perpendicular distance is 0. So to make this equation simpler, first we have to find out the forces whose line of action is passing through A, because that will not taken into that equation because their moment is 0. You see, this is the point, I dark it. So first you have to identify the forces, their line of action passing through A. So this is the point A actually. You see, 2 sine 30, the line of action is passing through A, so that will not contribute any moment about A. 2 cos 30, line of action passes through A, that will not contribute any moment. 1 sine 40, again its line of action, definitely that also passes through A, that also not contribute any moment about A. And you see, this 1.5 cos 45, its line of action is also passes through A, that will not contribute any moment. So the contribution of the moment at A, that is due to 1 cos 45, 2 sine 30, 2 cos 30 and 1.5 sine 45. So these 4 forces will contribute the moment at A. So first we pick 1.5 sine 45, this force. You see, this is the force line of action, this is the point, so perpendicular distance is 12. So that will be 1.5 sine 45 into 12, and it is clockwise, so positive. The second is 2 cos 30. This is the line of action of 2 cos 30. This is the line of action, and this distance from that point to the line of action of that force, the perpendicular distance, again 12 meter, and this also gives the clockwise moment. So that is 2 cos 30 into 12. The third is 2 sine 30. So this is the line of action of this force, again 12 meter perpendicular distance, but 2 sine 30, that will give anti-clockwise moment. So that is minus 2 sine 30 into 12. 1 cos 45, this force, the line of action of this force, again distance is 12, and that again contribute anti-clockwise moment about A. So that is minus 1 cos 45 into 12. So this is the left side expression. In the right side, the moment of the resultant about A, that will be R into D. Again it is clockwise, so R into D. So R, that is 0.5, already we determined. The left side calculation we do, and finally we are getting the value of D is 26.06 meter. So now the resultant is completely defined. Magnitude is 0.5 kilonewton, makes an angle of 45 degree, that is in the 4th quadrant, and that resultant is having the position, or you can say the perpendicular distance to the line of action of that resultant from A, that is 26.06 meter. So that is the complete representation of the resultant in the case of coplanar non-concurrent force system. So I think this video is really helpful to you to make your concept or to boost your concept of the resultant force. With that, I stop here. Thank you.